So yeah, let's get started. Thanks for coming to the first booth talk at OpenMP booth. And my name is Sangmin from Argonne National Lab, and I'm an assistant computer scientist there. And today, today I'm going to introduce our OpenMP brand new OpenMP implementation that's called Bolt, and that's actually OpenMP implementation over lightweight thread. Okay. So I think people here, most of people here are familiar with OpenMP, but let me briefly introduce OpenMP. What's OpenMP? So OpenMP is a directive-based programming model, and so we have sequential code like this, and you just augment that code with some programmers. Then the compiler, like this, the compiler will automatically translate this code to parallel code, and then your code will be run in parallel on a multi-core machine or many core machines. That's the idea, and we have many implementations currently, GCC or Intel implementation or LLVM Clang and so on. So, but recently we realized that these implementations are not very good at supporting nested parallelism or nested parallel loops. So we tackled this issue, and by testing some this simple code. So we have this for loop, and this is out loop, and then this is parallelized by OpenMP parallel for. And so we expect this code will be run in parallel on multi-core machine. But by accident, this code is using library, and that's called deep compute API. And so this code is calling this function, but inside this function again, it has loop, and it's using OpenMP to parallelize its own code. So at the end, we have this for loop, and inside this for loop, and then both are parallelized by OpenMP. So when we looked at this kind of pattern, and then we tested this code with different OpenMP implementations here, basically GCC and Intel compiler, and then basically we tested the extreme case. So we used all cores for the outer loop, and then we used other more thread for the inner loop that's used in the inside the function. Okay, sorry. So measure the performance of the previous code using many thread. Actually, we used the 36 thread for the outer loop, and that's basically using entire cores on the machine, because that we use the 36 core machine. And then we increased the number of threads for the inner loop, and then we noticed that the performance was dropping significantly. This is this log scale, the y-axis log scale, and then performance was dropping very significantly, even when we have 36 by 36 thread, and even the baseline case was less than 0.01 second, but it turned out at the end we almost have 2 seconds. And then we also tested Intel compiler, and even Intel compiler was performing better, because basically the difference is how they manage thread internally. So for GCC, they don't manage thread pool, they just create thread and they just destroy thread and then do it again and again. On the other hand, Intel compiler is doing much better. They do manage a thread pool, and then they reuse thread as long as they have some idle thread. So that's why they perform better than GCC, and in terms of absolute performance. But again, we tested, we manually translate this code to another threading layer, because we noticed that this performance came from the fact they are using pthread internally. So we use the different threading model to test whether how the threading model affects the performance, especially in this case. And so we used a threading model called Argonne. That's basically user-level thread library, and we used user-level thread instead of OS-level thread like pthread. So we manually translate the previous code to Argonne's code, and then we measured performance again, and the performance we improved this simple benchmark, the performance of this simple benchmark a lot, and basically the law is better. And these two are the performance that we obtained from using Argonne. So basically, my talk is about how we implement the OpenMP over lightweight thread or Argobos. Okay, so the Bolt, yeah, I'm going to introduce Bolt here. So Bolt is, we aim at a very lightning fast OpenMP implementation here. And even though it's not really lightning fast here, not now, but it's quite fast. And so Bolt, basically the name Bolt is a recursive acronym that stands for, Bolt is OpenMP over lightweight thread. So we have BOLT, but we still haven't found the proper word for V. So if one of you have an idea about V, then please come to me or email me. Then I really appreciate about that suggestion. So we have a website, and we just released the preview version of our software, so you guys can go and download and test it. So our objective for Bolt have three objectives. So the first one, we want to improve the nest massive parallelism with Bolt, and we also want to enhance the fine-grained task parallelism. And lastly, we want to improve the interoperability between OpenMP and MPI or other internal programming model. So in this talk, so far we have focused on the first objective, but since this is a research project and we are continuously working on this project, and so we'll address other two issues later. So basic approach of Bolt is we use the existing compilers, especially Intel compiler or Clang compiler, to generate the runtime code or the intermediate code from the OpenMP source code. So we use the existing compiler, but rather using the existing runtime code, we developed our own runtime using the same runtime API. So that means we kept the API compatibility. So you guys can use compiler as they are, but you just replace runtime with Bolt from Intel runtime or other GCC runtime, then your code can just run with Bolt. That's our approach. So to do that, our implementation is based on Intel OpenMP runtime API, and we basically modify the open source version of Intel runtime. And that's what we have done so far, and we plan to also develop or modify the Intel compiler to better support OpenMP runtime. That is our Bolt. Yeah. So let me briefly introduce Argobos because we are using Argobos internally. And Argobos is a lightweight, low-level threading and tasking library. And the philosophy of Argobos, basically, user-level thread is not a new concept. They have been existing for a very long time. But we realized that what they have tried is they want to replace pthread with user-level thread or any other threading model. But that's not, we realized that's not a good approach because the user-level thread and pthread, they have different characteristics and they have different usages. So, so our goal was, okay, let's try to provide threading mechanisms that's basically running on user space rather than try to replace pthread. So the philosophy of Argobot is, okay, we provide mechanisms but not policies. Even though we have some policies, we don't impose or we don't encourage the user to use our policies. So rather we recommend the user to develop their policy on top of Argobos mechanisms. So we explicitly separate mechanisms and policies, and then we support efficient mechanisms in Argobos. So this is a simple diagram of Argobos execution model. So we have many cores, multi-cores, and sorry. We have many cores. Is better. We have many cores. We have cores, and then we expose OS thread like pthread as execution streams. So we explicitly expose the first level of parallelism to the user. So user can control these execution streams, and on top of this execution stream, we also provide user-level thread and task list that can be mapped to these exchange streams. So you can explicitly manage this mapping or scheduling on top of OS thread, and everything is explicit. So that's the difference. And so with this flexible mechanism, you guys can implement OpenMP or Charm++, any other high-level programming models on top of this Argos, because we don't impose any specific policy to the high-level runtime. That's our approach. So we use this Argo bus to implement boards. So we have this kind of layer. So we have machine and we have Argo bus layer. And then on top of this, we have OpenMP layer. So basically, OpenMP thread and OpenMP tasks are translated to Argo bus user-level thread or task list. Then what's the difference between ULT and task list? The ULT is more or less the conventional thread. They have their own stack, and they can suspend and they can resume their execution. And on the other hand, the task list doesn't have the stack and cannot suspend this execution. So task list is just atomic work unit. So once you start this task list, you have to come to the end. So that's the difference. So in terms of overhead, so since task list has limitation, so it has less overhead than ULT. So our approach is, if it's possible, we use task list, but if it's not possible, or you don't have any idea about the code, then we use ULTs. That's our approach. And everything is mapped to, again, exchange streams. And so with this kind of mapping, we can handle nested parallelism or nested loops, just creating ULTs one task list, and we map them to exchange streams. And then the scheduler, internal scheduler that we developed, manages the scheduling or mapping between these two layers. That's our approach. So let me show the simple translation example. So we have this for loop again, and we have for loop, and this is parallel for loop. And the compiler, intercompiler or client compiler, just generate this kind of runtime core. And this is the fork core, so from the OpenMP parallel. And we kept this runtime API as it is, and then we implemented the runtime functions using Argo bus internally. So we create exchange streams if needed, and if they already exist, we don't create more exchange streams. And we create ULT and task list when we see these parallelisms or tasks. And then we execute these ULTs, and later we join all work units, ULTs or task list at the end. That's a simple idea. And again, this is just an illustration of our approach. We have exchange streams, and we create work units, and at the end we have some synchronization, like a barrier at the end.
I have a question.
Sure.
OpenMP is usually implemented by the compiler vendors,
Yep.
right? By the way, the Acrobat, where is the Acrobat? The Acrobat is implemented in OS or?
So Argo is a user-level library that we have developed.
Please repeat the question.
Okay, the question was, where is the Argo bus? And basically, Argo bus is not a part of compiler, but it's a part of library that we implemented. Actually, that's not exactly part of our library that I'm introducing here, but there's a separate library, but it's also learning in a user space, and it's a user-level library. And we integrate that threading library. The Argo is a threading library, and we integrate that library to our OpenMP implementation. Yeah. So again, our implementation is based on Intel's open source runtime library, and that is there. And we kept again the original runtime API as it is. So basically what we did was we designed and implemented the threading layer using Argo bus. Originally, the runtime was using pthread, only pthread, or other thread supported from OS, like Windows threads and so on. But we added this another layer, and then we also changed some internals to support OpenMP more efficiently with the Argo bus. Okay, then, okay, that's the just base approach. And how can you use Bolt? There are two simple ways. The first one, we support currently Clang compiler, Intel OpenMP compiler, and GCC. Because this is the same for the Intel runtime. Because Intel runtime already provides the ABI compatibility with these three compilers, and we kept that ABI as it is, so we can use these three compilers, and then so that means you just use existing compilers, but when you link the code, you use Bolt instead of Intel runtime or Gomf. Then your code will automatically use Bolt, and the Bolt can use Argobus pthread, but we recommend to use Argobus, of course. And that's it. Or the simpler way is to use LD preload. You don't need to recompile then your code. So you have your compiled version of your code, and when you execute your code, you set LD preload to the Bolt runtime. Then the runtime will be automatically used in your code. Yeah, there are two ways. Yeah.
Does Bolt also support features like task dependencies or the new task loop constructors?
Yeah, that's a good question. The question is whether the Bolt supports task loops or the task dependencies. The answer is currently we support task dependencies, but not task loop yet, because the original runtime has some limitations yet, and they haven't implemented everything. They implement task loop, but the compilers, not all compilers support task loop yet. Yeah, so that's why currently we don't officially support task loop, but we support task dependencies. Yeah. And this is some validation results that we used OpenUH OpenMP validation suite to test whether the Bolt is correctly implemented. And interestingly, even though we use the same compiler here, for example, Intel compiler, we got less failure than Intel compiler. The reason, I can tell you later in person, but I don't want to explicitly describe that. Okay. And this is again the Microbenchmark with Bolt. This is a manual translation, and these two are results from Bolt, because when we implement the OpenMP runtime, we had to add some more layers, and that causes some overhead. But we'll try to minimize this overhead continuously. But we have compared to the manual translation of OpenMP, and we have more overhead. And this one is using only ULT, and this one is using ULT as well as tasklet. And again, the tasklet has less overhead, and we got a better performance here. And these two are from GCC and again, Intel compiler.
What is ICC plus Argobus?
So this ICC plus Argobus means we manually translate the Microbenchmark that I showed before to the Argobus code.
So you don't go through Bolt?
Yeah, I don't go through Bolt. Right.
Just use the Argobus.
Right, exactly.
Instead of OpenMP.
Yes.
And then ICC plus Bolt will be OpenMP.
Yeah. The Bolt is OpenMP runtime. Yeah. And the next.
Sorry,
yeah.
one more question. It's all weak scaling, right?
No, this is not a weak scale. This is strong scaling, but we oversubscribe the machine. This is nested loop, and the
It's the number of threads for the inner loop.
number of threads for the inner loop. The outer loop was using 36 thread, and this is 36 core machine. Yeah, this is so just to see pure overhead of nested loops. Yeah.
Does the Argonne or the Bolt implementation also provide advantages in case you have not a nested loop, or is it only for nested loop?
So, okay, the question is whether whether our implementation provides some benefit for the non-nested cases. So, but my answer is we don't expect much of benefit, because with a single nested loops, most codes are compute bound, and in that case, the creation and destruction of thread, the overhead of those two operations is very little, and you cannot see the difference. Even though there's a difference, the magnitude of the difference is less than millisecond or microsecond unit. Yeah.
You do not expect to be worse with Bolt than you are with P threads. So
Sorry?
you don't expect a performance degradation with Bolt over P threads.
Right. Yeah. But yeah.
In your runtime library, you have working units like UNT and taskbeds.
Yeah.
And then there is a scheduler who is basically trying to manipulate in order to get performance. So what are the, you can say, main parameters to play with at your library to improve the performance? Like what is the main parameters for your library?
Okay. The question is how we could achieve better performance, and what's the main reason of getting better performance compared to the existing one. The main factor was because we used the lightweight thread library instead of pthread. So the cost of managing thread is much lesser than using pthread. That's the main factor. And in this case, the critical factor is we didn't actually oversubscribe the machine. Because if you create this amount of pthread, then basically you are oversubscribing the machine using many pthread. But with Bolt or with Argobus, we actually didn't oversubscribe the machine with OS level thread, but we create more user level thread. So that's not the real oversubscription. Even though we create more thread, and they only some number of threads are running in parallel, and some of them are not running in parallel. Yeah, that's the difference. Yeah.
So let's say you have some performance.
Yeah.
I'm pretty sure that that would not be the optimal performance. So if I want to improve the performance, what kind of parameters should I play with bolts that will give me extra performance specific to my OpenMP application? Like, do you have any study on this? Like tweaking your runtime rate?
Yeah, that's a good question. So the question is how we can tweak the runtime to get a better performance. But currently we have since we haven't touched the compiler parts, the compiler cannot do some magic for you. But we provide some additional interface to the user, so user can tweak something. That's the difference between these two. So basically, without user's hint or without compiler support, the runtime cannot know whether this code is safe to run with tasklet. Yeah. So because the tasklet has limitations, but if a user can provide that kind of hint, or compiler can pass that hint information to the runtime can exploit tasklets, and then you can improve this performance. Yeah. Yeah.
What operation is used for this test? What operation?
Basically, it's empty loop. Yeah. The operation is empty. Yeah, the loop body was empty.
Okay.
Yeah. So this is just to see pure overhead. Yeah.
Do you have some working examples for on your website?
Yeah. Yeah. Here it comes. That's a good question. So that's a good one. Yeah. So we have two application studies here. And the first one is the KIFMM test multiple method. And actually this code, the original implementation is using Intel MKL to offload the DGEM function. So, but the Intel MKL has sequential version and OpenMP version and so on, TV version and so on. But by default, the MKL disables the OpenMP support if the function is called inside OpenMP, because they don't want to handle the previous oversubscription and so on. So what we did was, okay, when we have more cores and when we have, additional hardware resources, and we enable this kind of nested parallelism, then how we want to see whether we can achieve better performance or any speed. So that's what we did here, and we set the number of cells for the application. This is for the outer loop, and to 9. Actually, we had 36 cores in this machine, but we just wanted to test whether we could achieve speed. And then for the MKL, and we increased the number of threads from 1 to 8. And actually the first 3 cases are not oversubscribing the machine. So the total number of threads here is 36, and this is 9, 18, and here 72. This is that the last case is the oversubscription case. So, well, for these three cases, even though we are not oversubscribing the machine, and the Intel runtime didn't improve the performance much. So only we could see a little improvement here. But we speculate that the reason was probably the management of thread, or they haven't optimized the nested loop cases. That's our speculation. But with Bolt, because we are using more cores for the Intel MKL, actually we could achieve speed up. We could reduce the execution time here, and even with oversubscription, we didn't lose performance much. So we almost kept the same performance as the previous cases. Yeah, that's the real use case, and so that's what we expect for the future applications, because we are getting CPUs that have more and more cores, and if we have a limited parallelism for the outer loop or in the application level, then we want to try to exploit more parallelism for the internal library or inner loops. Yeah. And this is another application, and this is the climate modeling mini app. And again, we tested actually this application is already implementing nested loops. Yeah, for the future user cases. And again, we see we could achieve better performance, much better performance than Intel runtime. Okay. Okay.
Intel runtime is supporting OpenMP for performance analysis.
Right.
Can we use OpenMP APIs to analyze the performance for Bolt runtime?
The question is, the Intel runtime is supporting OpenMP interface, but whether Bolt is also supporting that, currently no. Yeah, because currently we are not supporting OpenMP interface, because there are many issues. For example, we need to handle different threading libraries and so on. So that needs much work, and so we'll try to support, but that will take need some time. Okay, the last slide. To summarize, the Bolt is our new implementation of a lightweight thread. Basically, we use the Argo bus here, and we released the pre-release version, and you guys go there and download and test it. And this is Bolt team. The Bolt is mainly managed by Argonne National Lab, and there we have some collaborators. And the Argo board was developed by these guys, including me. And there are some pointers to the link, and we acknowledge our funding agencies. And actually, I'm working in the programming models and runtime system group at Argonne, led by Dr. Pawan Balaj, and we have many staff members and students and so on, and go in there and check some people there. And thanks for your attention.